All right, so we will continue on chapter 4. Any questions? All right, so we will study the different way of writing the chemical reaction equations. So let's continue on that, do this practice. So what we have here is two reactants in solution, in aqueous solution. One is the silver nitrate, and the other one is the potassium phosphate. So what we do, we're going to write the balanced molecular equation, then converting that to the complete ionic, and then finally get the net ionic. And that's our purpose. Okay? So we identify the ions in those reactants. Silver nitrate has silver. Silver is Ag1 plus. Nitrate is the NO3 negative. Okay? And potassium phosphate will have the K plus. And the phosphate is PO4 negative. So right now I really did not balance those charges. I just identify the type of ions. And so then you will use the ion, write up the formula for the reactant. Ag is 1 plus, NO3 is 1 negative, 1 ratio. So therefore, the formula for the first reactant is AgNO3. Then we were adding the state. It tells you the aqueous solution. So therefore, we see parentheses and AQ. Okay? Then we will write the second reactant. The second reactant starts with K1 plus and phosphate 3 negative. So we'll take the 3 as the subscript for K. So therefore, we have K3 and PO4. Okay? And the state is similar aqueous. When you have more than one reactant, you use plus. So plus together these two reactants. Okay? Now we will draw the arrow. See this produce what? So yeah. To predicting the product, I didn't ask you. So to predict the product, you are swapping the ions. Okay? So we will keep this color scheme, and we have a red and with green. So your products should have the same pattern. Okay? One product we're going to use, we're going to predict is Ag with PO4. If you take Ag with PO4, because Ag is 1 plus and PO4 is 3 negative, so therefore you have Ag3 PO4. And the state for Ag3PO4 is a solid S. The reason is you use like the solubility table, you will see this compound is insoluble. Insoluble means a precipitate or solid. Okay? And then we will see the other product. So we will take the K and we will keep this red with green and 1:1 ratio, so therefore we have KNO3. Okay? And you use the solubility table again, you will see KNO3 is soluble, so therefore we see the state is AQ. Okay? Again, you have more than one product and you will use a plus. So this is our equation, but not a balance. You can balance the equation by using the coefficient, and I will use 3 in front of AgNO3, then I'll put another 3 in front of KNO3. Okay? So now the equation is balanced, and this equation is the balanced molecular equation. Next, you want to convert, or starting from this equation, to get the second one, the complete ionic. So to do that, you first decide what of those reactant or product you are going to rewrite. Okay, so rewrite some of them as ions. You only rewrite those SE. I think someone probably still remember what I mean by SE. Strong electrolyte. Okay, which means either a strong acid or soluble ionic. Okay? So let's identify each one of these. The first reactant is the AgNO3. Is this a SE? Is AgNO3 a SE? Well, maybe I will tell you yes, then you tell me the reason. Well, why this is a SE?
You react the Ag with the PO4 is going to be insoluble.
Okay, so you will say you go by this two groupers of compound. Okay? So you will say if you want to see something is SE, you first identify is there something SA. SA is a strong acid. Okay? If not, then you identify is there something a soluble ionic. Okay? So either one will put your matter into the so-called SE. Okay? So AgNO3 is not a SA, it's not a strong acid, but AgNO3 is ionic and soluble. So therefore, AgNO3 will fall into this second group. So no matter the first group or second group, as long as it's in one of these two groups, and then it's SE. So SE, that means our answer is yes. We're going to rewrite this first one as separated ions. Okay. So then let's keep practice. What do you think about this K3PO4? Is this K3PO4 a SE?
No.
Any other comment? Is this a K3PO4 a SE?
Oh, yes. Soluble.
Yes, soluble ionic. Soluble ionic is one type of SE. So therefore, yes. Drink some vinegar. I just find out the solubility. I hiccup a lot. So I feel either drinking some like lemonade or vinegar, and it's smooth right away. We'll convert those like organic compound into ions, then it's soluble in water. All right, so the first product is the Ag3PO4. Ag3PO4, what do you think? Is this SE or not? What is SE? Strong acid or soluble ionic? Very good. So this is not a strong acid. It is ionic, but not soluble. So therefore, this one is no. Very good. And the second reactant, KNO3. Yeah. Yes. So why yes? Soluble ionic, not only soluble. Okay. So there are two words here: soluble ionic. Soluble ionic together, so is one group of SE. SA itself is one group of SE. So if you belong to any group, then you are SE. The second group live like both of them are kind of like two words. Acid, what acid? Strong acid, right? Ionic, what ionic? Soluble ionic. Okay. All right, so now we are going to rewrite those. We identify as SU. I write yes, yes, no, yes as separate ions. So you just write them as ions. I'm going to erase those. I hope you remember which one is SE. Okay. So I write 3 Ag1 plus. Okay. So where does the 3 come from? Cool. Yeah. So sometimes the coefficient will give you the number. So here the coefficient is 3, then the subscript is 1, so therefore 3 times 1 is 3. Okay? And then how many nitrate you are going to write? 3. Okay? Therefore plus 3 nitrate, NO3 one negative aqueous. And then we'll keep going on the second one. This time, sometimes you are making a mistake. You don't always go by what it looks like in the formula. So here the K3. But you don't write K3 together, you will write 3 K1 plus, okay? So therefore, we write like this. Okay? I didn't write something common mistake. I tell you, don't write like that. You don't write K3, something like that. Okay, so that's it wrong. Okay? And so you write 3 K1 plus. And then you will write the negative ion. So in this second reactant, what is our negative ion? PO4. and 3 negative, right? Yeah. So therefore, plus PO4, 3 negative. When you write them as ion, you have to show their charge. What are their charge? Are they +1? Are they -3? Okay. And then we will see those products. So the first product is Ag3PO4S. What do you think? Are you going to rewrite this as ion?
Oh, no.
No. Yeah. So you just leave this alone. You just copy this exactly the same way you have in the balanced molecular equation. Don't do anything about that. And then what do you do to the last product? You break them apart. Okay, and you will see how many K plus? 3. How many NO3 are negative? Yeah. So therefore, 3K plus equals 3 NO3 1 negative. Oops, miss a charge. So here will be -1. Yeah. All right, so now we finish our separation. If you keep tracking like all those coefficient subscript, your equation is still balanced. So this is so-called complete ionic, a balanced complete ionic. What you do next, you will identify some ion on the left side of this arrow, also on the right side. So just cross those out to get the next net ionic. So what do you think? In this complete ionic equation, which ion on the left and also on the right? 3 NO3. So we'll cross that out. Okay. What else? 3K. Okay. So 3 NO3 here cross out. Okay. And 3K cross out. Okay. And then what left over is 3Ag and PO4 3 negative produce Ag3 PO4S. This will be our net ionic. Okay. Yeah. So usually you follow the process. It's kind of like pro and con. Obviously, it's feel like take time, but you will avoid a lot of mistakes. Any questions? Okay, now I will show you the next type of chemical reactions, acid-base reactions. First of all, you want to know what is acid, what is the base. Okay, acid are substances that ionize in aqueous solution to form H+, and because H+ consists of only a proton, acids are often called proton donor or donors. Okay? And here are 4 examples of acid. So the first one is hydrochloric acid, HCl. Then the next one, nitric acid, and sulfuric acid, acetic acid. So those model has those ligand here on the right side. So the white spherical ball is the H atom, and then you see the other color representing different atoms. And so the first 3 are strong acids. So the first 3 is so-called the SA, strong acid. Okay. The last one is a weak weak acid. All right, and so bases are substances that react with or accept H+ ion. They increase the concentration of OH1 negative, which means hydroxide, when dissolved in water. Substances do not have to contain hydroxide to be a base. One good example is ammonia, NH3. So NH3 obviously don't have OH in the compound, but it reacts with water and take one H+ away from one water, turn that water into hydroxide. Then ammonia itself turns into ammonium ion, NH4 1+. So those are the a very simple definition of acid base. There are many scientists try to define what is acid, what is the base. So this is one way to define what is acid, what is the base. All right, and strong or weak. Let's say strong acid. Strong acid means completely dissociating water. A weak acid only partially dissociate. Strong base dissociate to metal cations and hydroxide ions in water. Weak bases only partially react with water to produce hydroxide ion. So just kind of completely and partially. So if something do something completely, and that is strong. If you do something partially, and then you are weak. That something is weak. So this table you probably want to memorize or write on your note. And those are the 7 SA. There are 7 of them, 7 SA. And here is 8 common SB, strong base. And you notice all those SB, actually, they are all soluble ionic. And that's the reason when we say, what is SE? We don't have to worry about are they strong base. We just say the SE either a strong acid or soluble ionic. So the so-called neutralization reaction are the reactions between an acid and a base called the neutralization reaction. And they are also metathesis reactions. So here we did not see too much. In the lab, there's a question about acid-base reaction. Your answer depends on what you like to answer. You can answer like simply like this, that will be enough. And you can also say after the neutralization reaction, what will be the pH for your solution, or how much you put them together. So those are some little details. But most importantly, you see what is the acid-base reaction? It's kind of a silly question, a silly answer. Just the reaction between acid and base. So that's acid-base reactions. And so when the base is a metal hydroxide, water and salt are produced. And it has more details. As can be seen from an example of the molecular equation below, so we have HCl is an acid, NaOH is the base, and it produces H2O, which is water, then NaCl, that's obviously the salt. You don't have to be always NaCl to be a salt. So any ionic compound is a salt. So now we are again going to practice those different ways to write equations. Okay. Molecular equation is given here. Okay. And what we did in the first example in today's lecture is identify which of those reactants, which of those products are SE. If they are, we rewrite them as a separated ion. So we'll do the same here. Okay. So let's say we want to identify the SE first. So SE are 2 groups of SE, SA or soluble ionic compound. Okay. So now let's examine one by one. Is HCl SE?
Yes.
Why HCl is SE? Yeah, so any of these 2 groups will be qualified as SE. So this is SE. Okay. So SE, that means, are you going to separate? Yes, you're going to separate. Okay. And next one is NaOH. Is the NaOH SE?
Yes.
Yes. Why is NaOH is SE? Soluble ionic. Okay. So therefore, yes, you're going to rewrite. Okay. Now the product H2O. Is H2O SE? No. So it's actually the Ne, non-electrolyte. So therefore, no. Okay. NaCl is NaCl SE. Yeah. So now you It's much better. So therefore, NaCl is Se. Why NaCl is Se? Soluble ionic. So now we know like that these four substances, three of them are Se. So therefore, we are going to rewrite the three as a separate ion. Actually, no. The reactant can be also like We or Ne. Yeah. So once we know like what is Se, what is Ne, I'm going to erase what I write here, and we are going to begin to write them as a separate ion for those Se. So if you separate this HCl, what type of ion you will get, and how many you will get? H plus, yeah, and Cl one negative. So how many H plus you will get? One. And how many Cl? Yeah. So therefore, we examine similarly for all the others. We will have this equation. Okay. So in this equation, everything are separated into ions except this water. Why we don't separate the water into ion? Not Se, right? Yeah, not Se. So if not Se, you don't rewrite. Okay? And so this is the complete ionic. So next, you just identify the ion that appears on the left side of the arrow and also on the right side of the arrow. If they do, you cross them out. Just like some number in your mathematical equation, on the left, on the right, so they will cross out. Right? So in this complete ionic equation, what ion that is on the left and also on the right? Cl1 negative, Cl1 negative. So let's mark them. So here's one, here's one. What else? Na. Okay. So those two pairs cross out. Then what's left over will be your net ionic. But sometimes you might have to simplify the coefficient. Okay? In this case, just take out these two pair of Na plus and Cl1 negative. So what's left over is your result, is your answer. All right, and actually this net ionic equation is really representative equation for any reaction between strong acid and strong base, no matter what is your strong acid. In this example, your strong acid is HCl. If you replace this HCl by HNO3, and you replace this sodium hydroxide by calcium hydroxide, so I will do some work, and you will find out your net ionic will be still the same. I think that's probably the one reason the chemists like to write those different way of equations. Right, and some of those neutralization reactions, they produce gas. Okay, it's kind of the product is not really expected. Okay? So some of those common reactions that is also acid-base reaction. Acid-base also called the acid-base reaction, also called neutralization reaction. Okay? So they will release some gas. Typically will be those carbonate and bicarbonate. So that's also the way like chemists speaking. So when they say like carbonate, that means anything has carbonate. When you say bicarbonate, that means anything has bicarbonate. So if you have something carbonate, sodium carbonate, calcium carbonate, just carbonate, okay, and you react with some like acid, and you will see fuzz or gas released. Okay, so here in this example we have calcium carbonate, which is a major component in like the shell of a crab or shrimp. Okay, and so therefore you take this calcium carbonate with a solid. So this is not a SE, right? And reacting with HCl, And you probably expecting this product is okay. So the other product will be the H2CO3, right? Because you do the metathesis and you swap in the ion. And so initially what you get is H2CO3, which is so-called carbonic acid. The carbonic acid, H2CO3, as soon as it's produced or formed, it decomposes into CO2 and water. So therefore, it's kind of not what you expected. Okay? So that's one type of reaction that will give the gas. The second one, in this sentence, is bicarbonate. So as I said, anything bicarbonate, sodium bicarbonate, potassium bicarbonate, and anything. Okay? And bicarbonate is this part, HCO3. Okay? So you take that, reacting with an acid, and again, you will produce the salt. Okay? Then you produce CO2 and water. And another type is anything kind of the, so this will be the sulfide, S2 negative, IDE, sulfide. Okay? Anything sulfide, like sodium sulfide, potassium sulfide, okay? Reacting with some acid, produce this kind of expected. You swap in the ion, and then this is also expected, but this is gas. And be careful with the last one. So this so-called smells like a rotten eggs, H2S. So we usually do that like in this CLCC on the outside of the third floor, and a little bit, and everyone smells as a H2S, like a rotten eggs. All right. Any questions? And so this question is which is the correct net ion equation for the reaction of aqueous ammonia with nitric acid? Okay, so you want to get the net ionic. As I said, if you are okay, you do like a few practice and you can always get the answer right away. You just go use your own procedure. Otherwise, I usually just write the reactant and product, get the molecular equation. Okay, so in this case, the molecular equation will be this, because we identify one reactant is ammonia. So ammonia is NH3. So ammonia is NH3. Then terrace is aqueous. So therefore, I use AQ for the state. And I write here as one reactant. Okay. Then tell you the other reactant is nitric acid. So nitric acid is HNO3. And it just tell you both are aqueous. So therefore, both the state is AQ. So therefore, we, okay, you are very polite. So this will be HNO3 AQ, and here shall be NH4 NO3 AQ. Okay, sorry for the misprint or the typo. Right? Am I right?
Yes.
Okay. And so now this equation is balanced, right? You have this amount of N, this amount of H, and this amount of O on both sides. Okay. So that what you do, you will rewrite this molecular equation as a complete ionic. So then you decide which one I'm going to rewrite as a separated ion. Okay. So I'm going to rewrite the first one as a separated ion. Are you going to rewrite this one as a separate ion? Let me see, here I'm going to say separate. So separate. So what's the answer for this first one? Are you going to separate this first one? Yes or no? No. Okay. Why no?
Because it's not.
Remember, we only separate SE, right? So we only separate SE. So if you separate, you separate SE. So this one is not a SE. Right? It's a WE. weak E. Right? And what about the second reactant, HNO3AQ? Yeah, so this is yes. Why? SE, or particularly is SE strong acid. So that's SA. So then what about this only product, this ammonium nitrate? Yes, the reason SE. What type of SE is this? Soluble ionic, right? So just try to use this approach. Okay, so your soluble ionic is SE, strong acid is SE. Okay, then we'll rewrite. Okay, so once we decide, the first one we don't rewrite, the other two we're going to rewrite. Let's rewrite. Okay, so I'm going to erase here. And if you rewrite, so the first one we did not do anything, right? The second one, again, that's a mistake. So there should be HNO3, and cross that out. Okay, and this one should be NH4. Cross this out, NH4, NO3. Okay, and this will be AQ. And then what should we change for? Well, there's a lot of mistake. And this, what is this equation? Yeah, this is the complete ionic. What should we change here in this complete ionic? What's wrong with this complete ionic? That's the CL. We don't have a CL, right? We don't have a CL. This CL should be what? NO3 minus. Yeah. NO3 minus AQ and NO3 minus AQ. Okay. Now everything is okay. So after we change the name and cross out the CL1 negative, and we write NO3 negative. Okay. That okay? Okay. Any questions? Right. So in this complete ionic equation with the red NO3, what is our common ion that is on the left side of this arrow, also on the right side of the arrow? What is the common ion? NO3. Okay, so we'll cross that out. Okay. So now we're really going to cross that out. So go away. So that what's left over will be our NH3 plus H plus and that. I'm not going to erase everything. Yeah. Right. So that's our answer, right? So here should be NO3 negative AQ. So therefore our answer is D. Question? Yes, NH3 don't have a charge. So this is a molecular. Molecular dissolved in water, and you can still see the state of the AQ. Okay? It's very similar as methanol, but a little different. Okay? So if you have methanol, which is CH3OH AQ, okay? And this is like 100% as this. Okay? Now this ammonia is not really 100% of this, because ammonia was like partly like ionized water, so like produce like those like hydroxide, and itself turn into NH4 plus. But because it's not really a strong base, so therefore we don't write them as any form of ions. Okay, so yeah, you're right. So here we just write that as a molecular formula, no charge. Yeah. All right, any other questions? All right, so do another practice for the reaction of phosphorus acid, H3PO3 and potassium hydroxide. Use phosphorus acid as a diprotein. Write the balanced molecular equation and complete ionic and net ionic. Okay? So obviously, it sounds, I think this question tell you kind of trivial, what is acid? If I tell you one is acid, the other one will be the kind of the base, right? So this is acid, and then this is our base. So in this acid, you can see there are 3 H, okay? So sometimes you classify the acid according to how many H they can ionize, okay? So if the acid can, to the most, can only give you 1 H plus, is monoprotic, okay? If it can give you 2 H plus, diprotic. So technically, this H3 Pu3 can give you like a 3 H plus. So technically, this one is triprotic. But this question just want to note, it can be other possibilities. So you don't want to use this as triprotic, you want to use this as diprotic. Okay, so like that, yeah. What do you think? What does diprotic mean? What is triprotic? 3 H, so 3 H plus, then di 2. Okay. Yeah. So now we'll just begin to write these 2 reactants. Okay? And because tell us we are going to use this acid as diprotic, which means you are going to take a 2H away, 2H plus away. Okay, so you replace 2H plus by 2K1 plus. So that's what we did. Okay, we take 2H away, so therefore we still have another H, so therefore we have HPO3. Okay. Then the other 2H is replaced by K2. So that in that way, the charge is still balanced, right? Because PO, so the PO3 is 3 negative. Okay. So now let me emphasize, so this PO3 is 3 negative. So if you know PO3 is 3 negative, obviously you want to get neutral, you have to have a 3 plus. Okay? So that 3 plus can come from just 1 ion, like Fe3 plus. Okay? Or can come from 3 ion, 3 H plus. Okay? Or 2 of them come from H plus, and 2 of them come from K plus. And here we have, say, 2 of them come from K1 plus, and 1 come from H plus. Okay? So this is one product. Okay? And you take the H away, so the H actually become H plus, right? And we take 2 of them away. Okay? And then you see your plus always reacting with negative, right? So the other negative from the other reactant is hydroxide. Okay? So each one of this, if I forget about this 2 here, okay? So each one H plus and 1 hydroxide produce 1 water. Okay? So that's the problem we later on going to balance. Okay? But anyhow, we know we take H plus away and put it together with hydroxide, produce water. Okay? So therefore this is the second product, right? So now we are going to balance, really to balance the equation. And how you balance the equation?
One K forward and 2 on the water.
Okay, so that will work. Yeah, so we'll put 2 here, put 2 here. Okay. All right, any questions? Okay, so this is our result. So this is the balanced molecular equation. Okay. So we did twice before to converting from the molecular equation to the net ionic. Okay, let's do it again. Okay, so that's how we started, progressive. Okay, and you have to give it some patience. Okay, and so let's first identify in this few substances here. Okay, we see which one you are going to separate.
The HPO3.
Okay, so you began to respond that okay. Separate what? Separate what? Separate what? And then answer is SE. Very good. So now you have to identify for each of them which one is SE, right? Well, be careful, be careful. You always drag me into that. So H3PO3. Remember the SE, we'll write that again. What is SE? SA or soluble. These are the, both of them have two words. It's soluble. Well, I dragged someone in there. Ionic. Soluble ionic. Okay? So be SA and soluble ionic. Okay? So the first one, what is the first one? Is the first one ionic or acid? Okay, is this a strong acid? Yes. Strong for you, not strong for me. So separate? No, don't separate. Okay, because it's a WE. So the first one is WE. Okay. All right, now the second one. The second one is the KOH. Is the KOH SE? Why is SE? Yeah, so yes means separate, okay, and SE. Right. So this is for this. Let me make a line here. Okay. So this is for first one, and then this for second one. All right, then let's go to the first product. What do you think about the first product? Shall we answer yes for the separate? Well, be careful. Why no? Well, what kind of compound is this? Ionic. Why is it ionic? That has metal. Okay? So ionic and it's soluble. So one way to see something soluble or not, you just go to the solubility table. Otherwise, you see anything has a K. Anything has a K. Anything has like a lithium, sodium, potassium, rubidium, cesium, the alkali, metal, ion, they are soluble. Okay. So therefore, this is SE. So therefore, we say yes. All right. What about water? No. Yeah. So water, water is nothing. I have plenty of water. So that is AE. Right, now let's do that. So let's write the complete ionic, and then we will erase those common ion on both sides and get the net ionic. Okay. So what do you think? Do you rewrite the first one? Do you still remember rewrite the first one? Not the first one. No, because the first one is not SE. Okay. So second one is SE. If you rewrite the second one, you will have a 2K plus and 2 OH1 negative. Okay. Do we rewrite the first first product? Yes. And you will have a 2K 1 plus and one of this hydrogen phosphide, because this HPO3 2 negative called the hydrogen phosphide. Okay. So that's ion. We have like we rewrite the first product as a separate ion, but we leave water as it is. Okay. So this is our complete balanced ion equation. Then we will cross out those spectators. So what are the spectators? 2P and 2K, right? Anything else? No, you have to match exactly the same. Yeah. That's it. So then your net ionic will have these two leftover reactant. One is a molecular, the other one is ion. Okay? But even though, as the last question was asking, even though this H3PO3 is a weak acid or moderate acid, it's to some extent it exists as ion. But we like kind of common sense. Everyone agree. If they only partly as ion, we don't write them as ion at all. Okay? So this partially can exist as ion in solution, but we just say if you are not really complete 100%, we just keep you as a molecule. All right, any questions? So next type of chemical reactions are the oxidation reduction reactions. In this picture, it shows you the reaction between metal and non-metal. So the metal is calcium, you see the metal, right? Non-metal is oxygen, oxygen is the gas, okay? And so the gas, oxygen like a floating and this metal surface, okay? And then they come in contact with the metal surface, then something happens, okay? Electron transferred, okay? So the electron transferred or the electron get out from the calcium atom and get onto the oxygen atom. As a result, calcium atom turn into calcium ion, Ca2 plus, and oxygen atom turn into oxide, O2 negative, okay? And then the calcium 2 plus is very, very strongly attracted to the oxide, and we produce this new solid, okay? The chemical reaction equation is written as 2CAS plus O2 gas produce 2CaO S. Okay? So if you examine this chemical reaction carefully, okay, before the reaction, calcium exists as atom. And that means they have the same number of electron, same number of neutron for each calcium atom. I mean, same number, I won't say neutron, same number of electrons, same number of proton for each calcium atom, right? Question? Yes. Yeah. So that's the typical trend. Okay? Metal in the chemical reaction usually give out electrons. The non-metal usually want to receive the electrons. And so that's what I want you to observe. You already observe that. And then you will say, if something lost electron or give out electron, and we see that something is oxidized. Okay? If something gain electron or receive electron, then something is reduced. So therefore, in this chemical reaction, calcium lost electron, so it's oxidized. Okay? And oxygen gain electron is reduced. Okay? And this is a very common, but not that common. Okay? So therefore, we have some of those mnemonic way to memorize those like patterns. The so-called loss of electron is oxidation. If you take these three red letters, you get a Leo, like a line, right? And line eat a lot, so therefore when they eat, they eat the gear, so Leo gear. Right. So this is very common, but do not really like cover everything, every those oxidation reduction reactions. So some of those oxidation reduction reactions, you don't see like clearly some atom lost electron and some atom gain electron. I mean, not like one electron totally go from one to the other, maybe partially, okay? So initially there's more electron closer to some atom. As a result, electron is a little far away from them. So that's also oxidation reduction reactions. So how do you know in those kind of reactions, who has been oxidized and who has been reduced? So we'll use a little different way to tracking that or to identify, you know, for some other reaction, you don't see clearly the electron transfer. Is that an oxidation reduction reaction or not? Okay. But if you see your reaction is oxidation reduction, you can see here we emphasize this reaction by using a dash between them. I mean, they must happen together. So something oxidized and something must be reduced in the same time. Okay? So therefore, to even emphasize more of that, we just take some of those words like from the RED from the reduction, and OX from the oxidation and make a new word I call it redox. So how we identify some chemical reaction that not between metal and non-metal, don't clearly show the electron transfer from metal to non-metal. We use the so-called oxidation numbers. And we already see it in this week's lab. So like yesterday you do the lab, right? So to determine if the oxidation reduction reaction has occurred, we assign an oxidation number to each element in a neutral compound or charged entity. So what is a charged entity? What do you mean by a charged entity? Oh, what we call that? What do we call that? Huh? What do you say? Ions. So the charged entity is just ions. Okay, so after you identify the oxidation number, so oxidation number sometimes also called the oxidation state. Isn't it nice? Use this word state, many different meaning, right? So sometimes called the oxidation number and sometimes called oxidation state. And once you identify the oxidation number for all the atoms in the reactant, all the atoms in the product, just compare them. See who has increases or who has been decreased. Okay. So if any element's oxidation number change in a chemical reaction, then the reaction is a redox. So we first identify either any change, then we see who is the increase, who is the decrease. So an increasing in oxidation number for an element indicating the oxidation of that element. Okay? And decreasing in oxidation number indicate reduction. I think that makes sense. Decrease reduction have some common meaning, right? So just remember one, then you know the other one. So this is the bookkeeping method. It does not always imply that the atom has this much charge. Okay? And then you try to either write those rules on your notes and practice. Okay? So those rules, this word, priority, which means which one you use first. Okay? So the rule appears first, you use first. Okay? I number them as 1, 2, 3, 4, 5. So therefore, the rule number 1 has the highest priority. Okay, but that will not really help you to solve too many problems. Okay, you can see the limitation for rule number 1. It talk about the element. Okay, so if you have something and you want to identify the oxidation number for something, and that something is an element, then you can tell the answer is 0. Okay. For example, if I give you this chemical reaction, okay, so in this chemical reaction, you have 2 reactants and 1 product. Okay. So these 2 reactants, both of them are element. Remember in chapter 1, we spending like a lot of time to identify the matter, are the element, are the compound, are the mixture. Okay. Now you see what is the purpose for that, right? So this Na is the element because there's only 1 type of atom, right? So Cl2 is the element only 1 type. Okay? So if you see something is an element and you want to see what is the oxidation number for 1 Na atom, 0. Right? What is the oxidation number for 1 Cl? When we talk about those, we usually want you to see the answer for 1 atom. Okay? So therefore, the answer for both Na atom and Cl atom, 0 oxidation number. Okay? So then we use rule number 1 cannot have answer for this NaCl because NaCl not an element. Okay? So then rule number 2. Okay? Rule number 2 is for the monatomic ions. You know what is monatomic, right? So this is monatomic, which means has only 1 atom in it. Okay? This is monatomic, only 1 atom. Okay? So if you want to identify the oxidation number for this element silver, and you are given silver 1 plus, then you can tell the oxidation number for silver for every one silver for each one Ag atom, it's just 1 plus. Okay? For each one zinc, probably I should not think for the Ag atom, just for each one zinc. Okay? For each one zinc is 2 plus. Okay? Now for this question, you get an answer for all of them. So what is the oxidation state for zinc? For this zinc here on the left side, 0. And the oxidation state for this silver on the right, 0. Okay. So now we know like all those oxidation number for all of them. So here's 1 plus, and here's 0, has 2 plus. Remember on last slide, I told you if you know the oxidation number for all those elements, then you can tell me which element has been oxidized and which element has been reduced. So in this case, which element has been oxidized? Zinc changed the number from 0 to +2. Which element has been reduced? The silver. Ag changed from +1 to 0. Okay? So that's the usefulness of knowing the oxidation number. Now, these only 2 rules. These 2 rules only can help you that much. Most of the problem you have will be something else. You cannot have answer for these 2 using these 2 rules. Okay, so you have to use this rule 3. So rule 3 kind of has like a lower priority, but kind of in the middle. So what that means, if you cannot find answer for your answer like this NaCl, okay, so you will come up with this rule 3. Just read this statement carefully. The sum of the oxidation numbers in a neutral compound is 0. Okay, so you don't know what is the oxidation state for Na, what is the oxidation state for Cl. You see, I have 1 Na, 1 Cl, and if I say the oxidation number for Na is Na, and the oxidation number for Cl is Cl, then I was using a mathematical equation, so just 1 Na plus 1 Cl is 0. Okay. If something is a polyatomic ion, you're still using the element symbol for the unknown number. Just get a mathematical equation and equal to something. Okay. So here we use Na. So I set up the equation like because in like 1 NaCl, I have 1 Na. So therefore I say 1 Na plus 1 Cl equals 0. So that means Na and Cl become our unknown, kind of our X and Y. Okay? So you have X and Y, you only have 1 equation, you don't know the answer for both of them. You just know that they have those kind of equation, right? So to get an answer for both of them, you will go to the, you already cannot use rule 1 and rule 2. Rule 1, rule 2 cannot give you any answer for this question. So therefore, you go to the next 2 rules. We altogether have 5 rules. Okay? So rule 1, 2, 3, 4, 5. So right now you are on 3. Okay? So you are go to number 4. But you start on rule 3, you don't totally forget rule 3. Okay? But you say 3 has a little higher priority. So rule 4, 5 has a little lower priority. If I find some answer, I need to come back. Okay? So when you come back when you have 1 unknown. You have 2 unknown, you find the answer for 1 of them, then you come back. If you have 3 unknown, you find the answer for 2 of them, then come back. If you have 2 unknown, you find the answer for 2 unknown, then you forget this rule 3. Okay? So for this question, we have 2 unknown. We don't know what is Na, what is Cl. We're going to go to rule number 4. So rule number 4 we did not show you yet, but I say rule number 4 will tell you Na is +1. Okay? So if you know Na is +1, then you just carry this Na back into this equation. Okay? So replace Na by +1, so I have this new equation. Now in this new equation, there is only something we don't know. So Cl is kind of X, right? You solve for X, then you know Cl is -1. Okay? So the rule 3 continue. If something you have is not a neutral compound like iron, a polyatomic iron, nitrate, so we know we have NO3 one negative, okay? And we cannot use rule 1 and 2 to tell, oh, N is 0, O is 0, and everything 0, or altogether -1. So we cannot use those rules. So what do? You are going to use this rule 3, setting up the equation like this. And obviously, you can set in this equation in a different way. So I can say like x, but that will give you too many something to like convert. X plus 3y equal to -1. Now you have to remember what I mean by x, what I mean by y, right? So to make this problem simple, I just use n for the number for n and use O for the number of O. So we don't have to use x and y. Okay? So therefore, the equation we get is 1n plus 3 times O is -1. So again, we have an equation. Can you tell me what is n, what is O? Not yet, not yet. So therefore, we have to go to like the next rule, which is 4. So for this particular program, you don't get any help from rule 4. Okay? So in this program, the next rule is rule 4. No help. Do not give any information for N and O. But you go to the next rule, rule 5, it will tell you, we don't see them yet. So O is -2. Okay? So once you get a -2, then we put it here. Okay? So we still don't know what is n, then n plus 3 times -2 is -1. Now is a mathematical equation. You solve this equation, you get n plus 5. Okay, so that pretty much use these 5 rules. Even though we didn't talk about those rule 4, rule 5, but those just helper. I call them helper. So they are helpers. So what is rule 4? Rule 4 has 4A, 4B. So 4A means like those group 1 metals like lithium, sodium, potassium, cesium, and rubidium. Okay, and then group 2 like beryllium, magnesium, calcium, they have +2. Okay? So then rule 5 is very tedious table. Okay, so if you go like the last question for NO3 negative, we come to this rule number 5. And we go, the rule number 5 has a priority. So we first say, do we have F? If we have F, we will give number for F first. We don't have F. Do we have H? We don't have H. And then we have O. So therefore, we give the O the -2. All right. So just again, let's see what we did for this NO3 negative. Right. So we first set up the equation. We say we cannot have answer from rule 1 and rule 2. We just say 1n plus 3O is -1. Right? So we go to rule 4, we don't have any help. We come to this rule 5, and you do a kind of elimination. So F cannot help, H cannot help, and then you say O. So once you get O is -2, then you put -2 here. Okay? You see that very important, right? If you go all the way, you forget about this equation you get from rule 3b, oh, I get O is -2. And then here something also can help you to get for N. So N is group 5A. And for group 5A, you want to sign that -3. Then that's totally wrong, right? So even size, you set up the equation from rule 3, then get as much help as you need it, but don't get all the help, then come back, and then you substitute the information back into the equation. You're solving for the last one you don't know. All right, so let's do practice. What do you think for this P205? We want to find the oxidation number for the bold phase, which means the P. So can you use rule number 1 or rule number 2?
No.
No, because this is not a free element, not a monotonic ion. So what are you starting from? 3A. Okay. So 3A, You are setting up the equation like 2p plus 5o is 0. Okay. So how do you know what is p, what is o?
Using the rule 5.
Yeah, go to the next rule. Rule 4 cannot help you. Okay, so rule 5. Rule 5 will give you what answer? O is what? -2. So from no answer, no info from rule 4, go to rule 5, get O -2. Okay, very precisely. Then what do you do with this O equal to -2? You substitute, you put it back into this equation. Okay? So let's do that. So substitute O equal to -2 into the equation. Then we're solving the equation for P. Okay? And obviously, you can also find information for P, use rule 5, but you don't do that because if you do that, you override the higher priority rule 3. Okay, so therefore, I skip that step. So after we put this O -2 into this equation, you solve that equation, you get P is +5. All right. Next question is NaH. So in this case, the Brophase guy is H. So you want to find what is the number for H? Oxidation number for H. Okay. Can you use rule number 1? Is this a free element? No. Is this a monatomic ion? Not ion at all, right? So we are going to start with rule 3A. So 3A, we just use Na plus H, because there's only one Na, one H. So Na plus H is 0. So what do you know? Do you know Na yet? You probably know, but you see, I don't know. Yeah. So this no, hold on. So this is the rule 3. So what is after 3? 4. So try 4 first. Okay. So where you get any information from rule 4? Why no? Yes. Na is group 1A. Okay. So what you get from rule 4A is Na is +1. Okay. Got you. So Na is +1. Then what do? You substitute this Na is +1 here, and then what do you get for H? -1. Yeah. All right. Let's do more practice. So we have this dichromate. So this name dichromate, ATE. Okay, it's a negative ion. Okay, can you use rule number 2? No, rule number 2 is for the monatomic. And here we have like 2 type of atom. Okay, right. So what do? 3B, set up the equation, right? So how many Cr we have? 2 Cr. How many oxygen? 7. So 2 Cr plus 7O is -2. So not 0, okay? So equal to this -2, okay? And this one is 0 because this is a neutral compound, okay? So here the -2, okay? Again, you have 2 unknown. You don't know what is Cr. You don't know what is oxygen. So what do we do? Yeah, so in this case, 4 cannot help, okay? So 5 will give you what? Oxygen -2, right? So oxygen -2, then you substitute this into this equation, and you solve this equation, what do you get for Cr? +6, yeah. Excellent, okay? So that's how you solve those problems. In this case, Sn. So you want to find Sn, and it's a neutral compound, not a monatomic ion, not an element. So I set up the equation. So what your equation looks like? Sn plus 4Br equal to what? Equal to 0. Okay. So we have this equation. Now what do we do next? Yeah, we use the next 2 rules, right? So rule number 4 cannot help. And rule number, this kind of go deep into 5, right? Go deep into 5 for the beer. No, you look at the number, rule number 5. What is rule number 5? The first one is for F, right? Do you see the rule number 5?
Yes, and then H.
Then H, then O.
Group 7A.
Yeah, rule 7A. Yeah. So group 7A, BR is group 7A. If group 7A so far you don't have answer, you will get BR what? 91. Yeah. So BR 91. Okay. And then you put it into this equation. So obviously you have a false negative. You want to get 0, so Sn is what? Right. So then see this, usually you already know oxygen is what? -2. Do you think that's the usual one? Okay. Let's say the usual one or not. Okay. So usually most of the compound has oxygen in it is -2. Okay. Now you don't use pre-justice. Okay. So we'll use a rule. So we want to find out what is number for O. What do we start? Where are we starting from? 3A. Okay. So what the equation looks like? BA plus 2O, 0, right? So BA plus 2 is 0. Okay. Now who is the first? Who is the first? If you go to rule 5, Ariana, right? If you go to rule 5, you will have O first. If you go to rule 4, you have BA first. So which one are you going to first? 4, because 4 is higher priority. Okay. So what do you get for BA? 2 plus. Okay. If you have 2 plus for BA, you put into this equation, you solve for O, that O is what? 1 minus, altogether 2 minus. So therefore you have like 1 minus. And that's obviously not usual. Usually you will have O with 2 negative. Quickly, what is the number for O? 0. This one. 0. Why is 0? Element.
Rule number 1.
Rule number 1, yeah. Element. All right. Any questions? So the so-called single displacement reaction are one type of redox reactions. And in most single displacement reaction, ions oxidize the metal element. For example, H plus is the ion, right? H plus oxidize magnesium in the picture below. Okay. Why we use this example? Because H plus is very common, right? Many acids can give you H plus. HCl can give you H plus. So therefore, we see this equation here, and here we use HCl. So HCl plus magnesium metal produce H2 gas and MgCl2. So the gas actually the bubble is hydrogen gas, right? And the ion initially in the solution is displaced or replaced by the new ion formed from the metal. So in this case, what ion is replaced by what ion? So in this chemical reaction, yeah, very good. So H plus is replaced by the Mg2 plus, right? And so if I show you the oxidation number under, and you can also tell me. So which one is oxidized and which one is reduced?
The H plus is reduced.
Very good. Right.
CL is the
CL, nothing happens to CL. Yeah. Oxidized. Yeah. Very good. So then this table give you a list and show you which one is more active. So we'll continue on this when we come back next week. Okay? Have a nice weekend. You want more? Tennis? Hold on, I did not starting the class.